Hi everyone, welcome back. In this particular video, we're going to start talking about the reactions of epoxides. Now, epoxides can undergo reactions under acidic conditions and basic conditions. So we're going to look at both of these conditions and what sort of reactivity do we observe? Are there differences in how an epoxide reacts under basic conditions or nucleophilic conditions versus acidic conditions? Now, unlike ethers, which the epoxides are related to based on the functional group because they both contain that oxygen atom, epoxides are very reactive compounds. And as you can imagine, this reactivity, this is attributed to the ring stream. Okay, the ring string, because it's a three-membered ring, which is a very strained ring. So that ring strain makes it a high energy compound, and so it can react under a variety of conditions. The ring would like to open because it's under a lot of strain. Okay. So under basic conditions, just to look at like the most simplistic ring opening of epoxides under basic conditions. So if we have an epoxide, and the simplest epoxide possible, which is ethylene oxide, if you react ethylene oxide with a base, again, the simplest base possible, sodium hydroxide, and this reaction is going on in water as a solvent. Now, what we get here, our product is ethylene glycol. Okay, this is ethylene glycol. So that's the product that's used for as an antifreeze in cars, actually, the ethylene glycol. Okay, so you can convert ethylene oxide into the ethylene glycol. So what's the mechanism of this reaction? Now, as you can imagine, we have hydroxide here. The hydroxide, as we know, is a strong base and a nucleophile. So it's a strong base, strong nucleophile. And the ethylene oxide or the epoxide ring here, since we have the oxygen connected to these carbon atoms, they are both electrophilic. So that's the electrophilic site in your molecule. Okay, so we have an electrophilic site here. Both of these carbons, they are electrophilic sites. So essentially what happens is, under these conditions, the nucleophile, okay, sodium hydroxide acts as a nucleophile and goes and attacks that electrophilic carbon. So it's an SN2 type of attack. So that attacks that carbon. As that attack happens, the ring opens up to push the electrons towards the oxygen atom. And so we get an intermediate where we have the hydroxide now connected to that carbon. And on the other carbon, you're going to have an alkoxide. Okay. And this charge here would be supported by, or would be neutralized by, the sodium ion. So that's the role of the sodium ion here. And subsequently now, the alkoxide that's generated, it can react with water, which is our solvent. So it can abstract a proton from water. And as you might notice, that would generate hydroxide. Okay, so it would pick up a proton, it would become ethylene glycol, and plus it generates hydroxide. So minus hydroxide is what you get here. And by doing that, you've generated sodium hydroxide again, and you've made ethylene glycol. So the reaction just keeps going here. So in some sense, this reaction is like catalytic in the sodium hydroxide because you're using water as a solvent. You don't need stoichiometric amount of sodium hydroxide for doing this reaction. Okay. So that's the general reaction, basically the ring opening So essentially, two steps are involved in this reaction. Okay, first step, or let me write like this. The first step is the attack by the nucleophile on the electrophilic carbon. And that's basically the carbon which is connected to the oxygen atom, one of the two carbons. But we will look at some regiochemistry issues later, okay? And then the second step is protonation of the alkoxide. Protonation of the alkoxide. So now, so ethylene glycol, is that the only possibility? Like, is this the only reaction that's possible? The answer is no. You can pretty much attack the epoxide with any nucleophile that you've encountered so far, or that we've encountered in organic chemistry. Okay, now let's go ahead and look at some of those reactions. What are possibilities? Again, not an exhaustive list, but some possibilities of nucleophiles that could be used in this reaction. Okay, so if we start with the epoxide, you can imagine attacking the epoxide with, let's say, sodium methoxide or any alkoxide. Okay, so use this as an example for any alkoxide: sodium methoxide, sodium alkoxide. And this reaction again might be done in an appropriate alcohol solvent. So if it is sodium methoxide, then the reaction would be done in methanol. Okay, and then you can imagine that the methoxide is going to come and do a nucleophilic attack. Let me draw the epoxide a little bit farther away so that we can show the attack at least. So the methoxide is going to come, attack one of these two carbons for ethylene oxide, okay? And the single bond between the carbon and the oxygen would open up to become a negative charge. And then, as you can imagine, that negative charge is going to get protonated by the solvent. So our product in the end is going to be OH and OCH3. Okay, OH and OCH3. Now, if it were a different alcohol, our product is going to be OH and OR based on what alkoxide we use. So it would change. Okay, and other possibilities, again, some nucleophiles that we've seen. You could imagine reacting this with sodium cyanide, let's say. Sodium cyanide. I'm just choosing another example for a nucleophile here. Okay, sodium cyanide, and follow this up with a water workup or an acidic workup. Okay, follow it up with an acidic workup. So we have sodium cyanide. That's the nucleophile. So in this particular case, the cyanide is going to come and attack this carbon, that bond going to open up again. And so our product now in this case is going to be alcohol on one end and the nitrile group now on the other end. Okay, the two carbons of the epoxide Those are the two carbons in our epoxide. And so on one end, you get the alcohol and you get the nucleophile on the other end, okay, among those carbon atoms. That's not all. We could even, so another nucleophile, strong nucleophile that we've encountered earlier is an acetylide ion. So you could react this with some acetylide. So I could react it with sodium acetylide and follow it up with an acidic or a water workup. And in this case, now the acetylide is going to come and attack this carbon, and then that ring is going to open up, and then finally the oxygen gets protonated. So that means in my product, there will be a hydroxyl group, the two carbon framework, and then I will have the alkyne. So I can create a molecule with an alkyne in it and a hydroxyl group in it, right? There's a molecule with an ether and a hydroxyl group in it. So if you look at it, in some sense, what we're adding to our nucleophile, okay? What we're adding to our nucleophile is adding a CH2, OH to the nucleophile. That's what we're doing here. We are adding a CH2, OH to every nucleophile that we are using here. So that may be a functional group or a moiety, a chemical structure that you want to recollect so that you can use this in synthesis. So whenever you see a synthesis problem where you have something that can be a nucleophile and you've added a CH2, OH group to it, that would tell you, so two carbons and a hydroxyl group to it, or you've made an alcohol with two extra carbons, that will tell you that, okay, I need to use an epoxide. Okay, and again, just to capture a few more possibilities here, okay, we can react this with lithium aluminum hydride and then follow it up with an acidic workup. Okay, so lithium aluminum hydride and then an acidic workup. The hydride from the lithium aluminum hydride, right? The lithium aluminum hydride is a source of hydride. That's going to come and attack this carbon, the electrophilic carbon. And so that means my product is going to be the alcohol with that, where we've actually added a hydrogen to it because that was the nucleophile here. Or to bring in a more recent nucleophile that we've seen would be a Grignard reagent. So you could bring in a Grignard reagent, sorry, 1 and then 2. So you can bring in a Grignard reagent. This R is a nucleophile. That R is going to go and attack that carbon, and then the ring opens up. So that means my end product, or that our end product is going to be an alcohol with 2 extra carbons compared to what's in the alkyl group. So you can see how this is a very versatile sort of a electrophile for various nucleophiles. And your end product, you're going to add 2 carbons and a hydroxyl group in every case here. Okay. Next, we're going to talk about some of the regiochemistry and stereochemistry issues. So far we've used ethylene oxide, which is a symmetrical epoxide. Both of these carbons are identical in nature. What if they're different? Okay, what dictates the regiochemistry of the attack? That means where would the nucleophile attack? Okay, and things like that. Let's discuss those. So these were just some examples. Like I said, possibilities are endless because you could bring in any nucleophile and then quench it with water or do a water workup or an acidic workup on it to get the product. Okay, so regiochemistry under basic conditions. In fact, we are still operating under basic conditions, so we don't really need this. So we're going to talk about regiochemistry, okay? And regiochemistry deals with the question of where will the nucleophile attack? That's the question that we're trying to answer here. Attack and where will the nucleophile attack in case of an unsymmetrical epoxide. So if it's an unsymmetrical epoxide, where is the nucleophile going to attack? So let's use a simple example here. Of that epoxide, but now I'm going to add a methyl group on one of the ends. Okay, so it's not a symmetrical epoxide now. You can notice that this carbon here is del positive. That's electrophilic because of the oxygen, which is del negative. And the other carbon here, this is also del positive. So there are two electrophilic sites now, and they're not identical, unlike the ethylene oxide that we were dealing with. So now the question is, if we were to use this epoxide and a nucleophile were to come and attack, okay, where would it attack? Is the nucleophile going to attack on this carbon here, okay, the carbon on the right, or is the nucleophile going to attack the other carbon here? Do we have any rationale for this based on what sort of attack is? And if you remember what sort of attack it is, this is, as I had written earlier, this attack is an SN2-like attack. Okay, this is an SN2-like attack. So that should help us rationalize which of these two carbons would the nucleophile attack. Okay, and the answer would be the nucleophile will attack the less substituted carbon. Okay, so between these two carbons, the carbon on the right, that's less substituted. So that means this would be the preferred attack. This attack will not happen. Okay, the nucleophile is going to attack the less substituted carbon, and then the ring would open up. So let's look at an example of what the product would look like if we were to do this. Okay, so let's use this epoxide, or we can make it slightly longer because now it really doesn't matter, right? So we can make it another epoxide. I've added another carbon to it, and we react this epoxide with, let's say, sodium cyanide to keep it simple. And we are going to follow this up with a water workup. So in this particular case, the cyanide is going to go and attack that less substituted carbon. The ring would open up, okay? And so the product that we get in the end is going to look like that. The hydroxyl would be on this end, and the cyanide would be on the other end. So this oxygen is connected to that carbon. So if we were to number these carbons, let's say 1, 2, 3, and 4. Here we have 1, 2, 3, and 4. So you can see how the oxygen in the epoxide becomes an alcohol group on carbon number 2 after the protonation step. So I haven't written the entire mechanism here, but after the protonation step, it's going to become the alcohol on carbon number 2. and the cyanide came and attacked carbon number 1. So it is connected to carbon number 1. Okay, let's look at another example. If you were to consider a nucleophilic attack, so let's say we have an example like this. Now you can notice how this carbon here is secondary in nature, while this carbon is tertiary in nature. Okay, one is tertiary, one is secondary, and the other one is a tertiary carbon. So if we react this with sodium methoxide, let's say, in methanol, and again, I'm just choosing a nucleophile, a random nucleophile here to show the attack. Because we have the less substituted carbon here, the methoxide is going to come and attack this carbon here, and the ring would open up. Okay, so that in the end, we will get the hydroxyl here. That carbon would have the 2 methyl groups to it, and then you're going to have the methoxide connected to that carbon. Okay. In fact, there is something more that we're going to talk about this example here. There's like another aspect of this attack that we can talk about in this particular example. But right now, I just wanted to show the regiochemistry of the attack. So the attack happens at the less substituted carbon when the nucleophile is attacking an epoxide. Okay. The next aspect of nucleophilic attack on an epoxide under basic conditions. Okay. And in case this is confusing, read the basic conditions as with a nucleophile. Okay. It's an attack with a nucleophile because your strong nucleophiles are usually strong bases. Okay. The second aspect of this attack that we are going to talk about is the stereochemistry of the attack. And for showing this, we have to talk about, okay, what the question we're trying to answer here is, what is the stereochemical outcome of the attack? What is the stereochemical outcome of the attack? Okay, how does the attack affect the stereochemistry of the epoxide or in the product? Okay, how does that change the stereochemistry? So for this, to sort of demonstrate this, I'm going to use an epoxide where we are now going to track the stereochemistry. Okay, so I'm going to put 2 methyl groups here, so there's no stereochemistry here. Okay, but on this other side, I'm going to actually show some stereochemistry. So let's say we have an ethyl group there, and that ethyl group is on a wedge, which means there is a hydrogen on the dash over there. Okay. And now if we consider the attack with the base, so going back, or the nucleophile, going back to the example that we were just working on. So let's say if this epoxide is attacked by a nucleophile, okay, sodium methoxide and methanol. And we already said that this carbon is tertiary, this carbon is secondary. So based on regiochemistry, the attack must happen on this carbon. Okay. So when the nucleophile comes and attacks this carbon, we've already classified this attack. This is an SN2-like attack. So since it is an SN2-like attack, the attack must proceed with an inversion of configuration at that carbon, because whenever an SN2 attack happens, the configuration inverts. So all of those principles that we learned for alkyl halides, they still apply because we're working with an SN2-like attack here, okay? So the answer here is inversion of configuration at the site of attack, okay, at the site of attack. And I'm going to clarify that using another example. So inversion of configuration at the site of attack. So when the attack happens here, we are going to get the ring open up. So now the oxygen would have three lone pairs, one negative charge to it. The two methyl groups are here, and the methoxide attack from the bottom here. So I'm going to draw the methoxide at the bottom here. And this ethyl group, which was on a wedge pointing down, now I'm going to put that wedge bond up. Okay, and the ethyl group is there, and the hydrogen is here. And in a subsequent step, right, this is not the product yet. So in a subsequent step, the alkoxide here will get protonated. The negative charge here gets protonated from the solvent so that we generate more methoxide in some sense. Okay. So we will get a hydroxyl group here. Got that. We've got OCH3. And we've got the hydrogen over there. So that would be the final product. So did the configuration invert? Let's go ahead and verify if that really happened. Okay. If I focus on this carbon here, which was a chiral center, and if we assign a configuration to this carbon, we're going to say that this oxygen was 1. Okay. That's the highest priority group on this carbon. The hydrogen is 4. And then we have this carbon and this carbon. So this will be 2 and this will be 3. So that's the priority assigned to all of those groups. So now if you look at it, and going from 1 to 2 to 3, this is a counterclockwise rotation, which means the configuration of this carbon was S. So it was an S configuration, and the lowest priority group is on the dash. Coming to our product, we have to assign configuration at this carbon here because that's the carbon in the epoxide. So if you look at it, again, oxygen is going to be 1, hydrogen is 4, this carbon is 2, and that carbon there is 3. And now if you look, and going from 1 to 2 to 3, sorry, I should do it on the product here. 1, 4, 2, and 3. But when you look at it, in going from the highest priority group to the second to the third, we are moving in a clockwise direction. So that means the configuration of this carbon is R. So the configuration has inverted at the site of the attack. Okay, wherever the attack happened, the configuration has inverted at that carbon. I'm going to use another example to basically drive this concept home. Okay, an example where there is a chiral center on both carbon atoms, and then we will make sure that the configuration only inverts at the site of the attack. That's what we mean here, because there's no attack happening on this carbon, so the configuration need not invert there. Okay. So the final example here for the attack under basic conditions. So we will keep the ethyl group the same here. Okay, so let's say we have the ethyl group there. There's a hydrogen over there, but on the other carbon here, let's say that there is an ethyl group on this carbon, and there is a methyl group on that carbon. Okay, there's an ethyl group, and there's a methyl group. So now we are looking at another carbon, which is chiral. Okay. And let's go ahead and assign the configurations to these carbon atoms. So for the first carbon here, we had already assigned a configuration. That does not change. You can verify that. So this carbon is of the S configuration. Okay. For the carbon on the left-hand side here, if we assign priorities, oxygen is 1. Oxygen is 1, and of the carbons that are there, this carbon here would be 2. This carbon would be 2. You'll have 3 and then 4. So the methyl group is going to be the 4th priority group. So if you look at it going from 1 to 2 to 3, this is still a counterclockwise rotation with the lowest priority group on the dash. That means this carbon is also an S configuration. Okay, so they're both S configurations. And now if we attack this with sodium methoxide in methanol, I'm just keeping that constant so that we can compare it directly to the previous example. Okay, if we do it, and I'm going to write down the product now, and again, I will show the electron push, the attack, because the methoxide, remember, comes and attacks this carbon. That's the less substituted of the 2 carbons here. So the methoxide is going to attack that carbon. The ring is going to open that way. So that in our product, we would have, when everything is done, I'm not showing the alkoxide now, but when everything is done, the oxygen would be on this carbon. On that carbon, we should have an ethyl group. There should be a methyl group on that carbon. It's connected to the other carbon, which has the methoxide on it, and the ethyl group, and the hydrogen. So we've already assigned stereochemistry to this carbon in the previous example. And what we found is that this stereochemistry was R. Okay, so there was an inversion of configuration there. But if you look at the other carbon, which was not attacked, okay, so the carbon that was not the site of the attack, on that carbon, this is 1, there's our 2, 3, and 4. So if you look at it, the configuration, oh my God, okay, sorry, my bad here. This configuration here was already R, okay? It was a clockwise rotation. I assigned it incorrectly at that point. Okay, so the configuration here is R, and then in the product, the configuration, it is retained. So that still remains R, okay? So the carbon where the configuration, or the carbon which was not attacked, the configuration of that carbon is retained. It remains R in the starting material and the product, but the carbon where the attack happened, the configuration there gets inverted. It goes from an S to an R. And I want to make sure, yes, it is correct. Okay, so I hope those examples were useful in seeing how versatile the nucleophilic attack on an epoxide is. And in every case, what we noticed is the product was an alcohol with 2 extra carbon atoms. Now, if you use an asymmetric or like a different epoxide, you're going to add more carbons, actually. We were talking about the specific example of ethylene oxide there. Okay, and then we talked about the regiochemical aspect of the attack, which says that the attack would happen on the less substituted carbon because this is an SN2 kind of attack, and the stereochemical aspect of the attack, which tells us that the configuration must invert at the site of attack because this is an SN2 like attack. So I hope everyone finds this video useful. Bye.